Alright, so we discussed the techniques to reduce the switching power so far. Let's turn our focus to leakage power control, the techniques and technology and the design architecture techniques that we apply in semiconductor chip design to reduce the leakage power. Okay, so CMOS threshold voltage VT is the main control entity for leakage, for CMOS leakage, and as the technology node is scaling, right, the channel length is reducing. The effect is that the drain to source, the VDS, the voltage that we applied at the gate, and the threshold voltage drops, reduces. Okay, so lower the channel length, lesser the threshold voltage, which in turns affects in higher leakage. So in general, as we do the technology node scaling, leakage will increase. It is not increasing up to that extent because we are deploying techniques to control leakage that we will discuss, but as far as fundamental is concerned, with the reduced gate length, threshold voltage reduces and the leakage will be more. VT, the threshold voltage, right, we can control that, but high VT will directly impact in slower circuits because the delay of the circuit will increase. As threshold voltage will increase, the current through the transistor reduces, delay becomes more, the circuit becomes slower basically, right? We cannot operate it at higher frequency as for if we just increase the threshold voltage. So we need a trade-off or some smart way of using it both, so that where we want to reduce the VT for faster circuit, or where we want to increase the VT to control the leakage, but at the expense of slower circuit. So how that we will do intelligently, we will see in coming slides. Okay, so before that we want to discuss some more fundamentals. Okay, suppose we have a gate length L and width of CMOS W, and that is defined. Then another factor that is with technology node scaling is happening is that reduction in the thickness of this oxide. Okay, and one more thing that is happening at the same time in the technology, we will see why we are doing that we are decreasing this size, this depth. We are decreasing the depth of drain. Okay, so these are two parameters. Just as a fact, we are let's keep it in mind. Okay, so what is happening, this VD, as this length is decreasing more and more, there is more and more effect of VDS on this channel. Okay, and this effect is causing one thing that is called VT roll off. Okay, and with that VT roll off, the leakage increases. Okay, in order to counter that, we decrease the oxide thickness so that gate comes back into the control. Okay, there is less impact of VDS on the channel below the gate, and that's why thinner and thinner dioxide is applied when we reduce the gate length. And some of the technique that is applied is reducing this depth, that also counters this effect of that is called VT roll off. Okay, and VT roll off is directly impacting my leakage. Okay, so in order to control that, when the gate length is we are reducing for the reasons we already discussed for switching power. The leakage we are controlling by reducing the thickness of the oxide layer and reducing the depth. Okay. Reducing the oxide thickness brings another problems that is also solved. Okay. We'll see. What in this picture is seen here, this COX and CD is in a way shows the effect of coupling between for the drain, and as I say, with XJ reducing, CD reduces. It means that when this depth is reducing, the CD is reducing. Its effect, its coupling is reducing. Okay. Same way TOX, the thickness is reducing, then COX is increasing, sorry, right? So COX is increasing as this thickness reduces, then its coupling increases. So gate comes back into the control of the channel, right? And there is less effect of VT roll off. That's the fundamental I tried to explain. So while we scale the technology node for benefits, we already discussed about the dynamic power and high speed that brings the higher leakage, but we control by using these technologies. Okay. Just for the knowledge sake, there's some additional things those are done basically to control the VT roll off, the same thing that we were discussing, that is called shallow junction extension. Again, that does the same thing. Okay, that the drain will have lesser effect on the channel below the gate and VT roll off factor will be reduced. Now comes to other part, that as we were making the gate oxide thinner and thinner, there were problems of tunneling current because of very thin silicon dioxide, SiO2. So that is taken care by using high K dielectrics. So what it does, that the high K dielectric, the layer will be not so thin, it will be thicker, but the thicker layer will be equivalent of very thin SiO2 layer, equivalent of. Okay, it gives the same effect on the gate. So with the thick high K dielectric, the tunneling current, leakage current problem is solved, while it still gives the same effect of very thin SiO2 layer. Okay, so this is about the manufacturing technology, just for the knowledge. Okay, so we discussed about the technologies, the CMOS technology so far. Now we will discuss about in the design and architecture the things that we do in order to control the leakage. Okay, so there are some known technologies and techniques, like for switching power you will do clock gating, like when the clock is not there, switching is not happening, switching power will not be there. In order to control the leakage, we will have to power gate, right? So that, but that we will see how we manage that. We cannot always power gate, right? When while circuit is not in use, you can power gate. Even when you power gate, there is penalty of larger or higher wake up times, but we need to consider all that. But before that, while the circuit is operating, right, at the same time leakage is also happening. So there are multiple other techniques in which are deployed. Transistor stacking is one technique. Multi VT architecture, the threshold, like there will be different cells of different VT, threshold voltage, and we optimize in a way, making use of both the volts we discussed earlier, right? So lesser VT means high performance, high speed, and but leakage is more. So where we want to control the leakage, the high VT transistors will be used. Okay, and variable VT CMOS. So we can actually vary the threshold voltage of CMOS at the runtime, and that is done using the body biasing, and there is gate length biasing, because gate length can be slightly biased, and that affects in the leakage control, right? So that we will see. And voltage scaling, that if before power gating you can scale the voltage a little bit, where you are just retaining the states, right? Or you want lesser performance and you go to a slightly lesser voltage, right? If the circuit is on a halt and VDD mean conditions, right? So those techniques are voltage scaling. Then circuit is on but voltage is minimized, then that scaling is further reducing the leakage current. Okay. Dynamic VT scaling we discussed. Okay, at the runtime, there are some techniques which are deployed. So at the runtime, there is one technique in which VT can be scaled. So we will see in coming slides there are a different type of body bias which can affect the VT of the transistor, and that can be done on the runtime. So as we discussed the transistor stacking part, so a multiple input gate is, if it is realized right in this manner, so what happens, this in this case the leakage current reduces, right? So that is because of negative gate to source voltages and the body effect is there. And suppose if we just had one CMOS of one transistor and one PMOS and one NMOS, there will be higher leakage compared to this circuit, where in the series there are three NMOS are there and the leakage current will reduce. That is one of the architecture that is used in the silicon technologies to reduce the leakage current. Okay, so gate length biasing, as we were discussing, in the circuits there can be some of the critical paths, some non-critical paths. Some non-critical paths where there is some margin to increase the delay, and there we can take just advantage of gate length biasing. So you can increase the gate length a little bit, and very marginally, right? So it's biasing only, and but that gives multifold advantage in reducing the leakage in those circuits. So where there is a margin available, you make use of it. And there are dual VT CMOS. So dual VT CMOS are high VT and low VT. That's how we put in the circuit. Mostly like power getting CMOS, those will be high VT, because we want very less leakage through them. Body biasing is VT control. For threshold voltage control, there are two types of body biasing, either reverse body biasing or forward body biasing. Okay, and in case of forward body biasing, the VTH will be low, and the reverse body biasing, VTH will be high, which will be used in the sleep mode. And this is useful in the active mode, because with the forward body biasing, VTH will be low and we want a circuit to be faster. Okay, so at the runtime this VT control can happen, and while the circuit is in sleep, we want high VT so that leakage current is less, right? So that's the intelligently we use of this technique. While we save the leakage power, at the same time we make the circuit faster with the forward body biasing while it is operating. In the sleep mode, we configure it in such a way that with the reverse body biasing, in the sleep mode the leakage becomes less and less with the high VT. Same concept that we were discussing. So reverse body bias and forward body bias, and in the active mode, reverse body bias in the idle mode for the reducing the leakage current. All right, so In the next chapter, we will discuss power gating. So far, we discussed the technology, the CMOS technology and techniques in architecture and design which are there, which are implemented in SOCs and semiconductor devices to reduce the leakage current or leakage power. Okay, we take a pause here and then we will resume with the power gating circuits and more knowledge about the power gating, and which is ultimately done to completely um, reduce the leakage current.